all of this might naturally lead us to the question, okay, so I've sort of given you a motivation for why we use a device tree, but is the device tree essential? Because after all, I mean, certain parts of the kernel code I can think of as essential, right? I mean, I have a bootloader whose job is to basically take the entire, the initial part of the code, load it up from, let's say, a SD card, put it into a certain location of memory. I also have certain things such as drivers whose job is to actually sort of understand how to modify the registers being used by a particular hardware device and make it behave in a certain way. All of those are what we would call essential code. Now, in that sense, is a device tree essential in order to boot up a Linux system? Well, it's a probably the wrong question to ask, right? But having said that, let's look at where exactly we need a device tree. Let's say I was writing bare metal code. What do I mean by bare metal code? It means I don't have an operating system. The example that we saw earlier, right, where we basically just compiled an ELF file, loaded into a specific location in memory and let it run, right? Bare metal code can pretty much means that we have direct access to everything that's there in the system. We do not have an operating system whose job is to sort of virtualize memory addresses and provide protection between different kinds of processes that are running in the system. And if that's the case, maybe we don't really care too much about a device tree because we know enough about our hardware system that perhaps actually putting in the hard-coded memory locations may not be a very big deal, right? Of course, what it means is this is not scalable. You can do this perhaps for a fairly limited small piece of software running on one particular platform, but trying to run it on multiple platforms and trying to increase the complexity of the software will become difficult very soon. Now, the other thing that I need to mention over here is that, as I said, x86 systems, most likely the laptops that most of you are using or desktops, anything that has an Intel or AMD processor in general, right, uses a different approach. It uses something called the Advanced Configuration and Power Interface. You might have come across the term ACPI at some point. That's basically what this stands for. Now, this ACPI interface has to be provided and initialized through the BIOS of the system. Now, once again, what's BIOS? It's just some kind of first level boot code that is there in the flash memory present on the motherboard, and literally that's what starts up even before I actually start reading from a disk, right? And that flash memory contains information about ACPI, the Advanced Configuration and Power Interface, and that by probing that, all the information corresponding to a particular motherboard and the devices connected on it is pretty much stored over there, right? And not just that, it turns out that there are other kinds of buses. The most common one that you have probably come across is USB, and some of you may have also sort of had opportunity to actually work with PCI based cards. Most of you are almost certainly working with some kind of PCI devices, but you might not actually have gone and removed a card or seen how it connects to the motherboard and so on. But PCI is a set of sort of slots into which you can plug in cards. Definitely more complicated to use than something like USB, but having said that, it typically provides like higher speeds and so on, which is why it is required, especially for graphics cards and so on. Now, both PCI as well as USB follow a different approach, right? They don't require you to go and modify something like the device tree in order to detect a new device. What you can do over there instead is they follow what's called a self-enumerating approach, which means that when I actually plug in a new device on the bus, there is some kind of hardware and software combination or firmware combination inside the bus itself, which is able to detect the new device and assign addresses to it and make it accessible to the rest of the operating system. Bottom line is x86 based systems do not use the device tree, right? So, having said all of that, most non-x86 systems, in particular ARM, which is probably the most common, and nowadays RISC-V, when they are booting into Linux, right, the management of these systems is best done using a device tree. Now, why am I saying best done? Once again, the point is it's not mandatory. It is possible to get Linux booting on the system without using a device tree. It's just that it will be extremely difficult to adapt from one system to another, right? So, the device tree sort of is more an ease of use approach, but on the other hand it also tells you a lot about the system and helps to sort of have code which generalizes across multiple different boards. So with all of this in place, what I am going to do now is to actually look at an example of a device tree and try and understand a little bit about the various different parameters or words, the keywords, the structures that are present in there, right. One thing I want to emphasize, and I will repeat this again and again, the purpose of this is not for you to be able to write new device trees from scratch, right. What you are, what we hope that you will be comfortable with, right, as part of this process over here, is understanding what a given device tree implies, and if necessary making the changes required in order to attach a new device onto an existing system, right. And the reason I am saying that is because, as you will notice once I show you the full device tree, an actual complete device tree from scratch can look very complicated, right. So having said that, right, there are a number of words over here that are highlighted. I want to sort of say, okay, can we understand a little bit more about what's going on, right? Can I look into the device tree specification, right, and understand this? Now there are a couple of different terms that I need to specify, right. There is the DTS, which is the device tree specification, which is a text based format. That's the one that I will be showing you now, right. On the other hand, text is good for humans because we can read it, but it's actually a wasted way of representing information for a computer, right. Computers would much prefer that the text or the strings that you have over there are sort of smashed together. You don't leave unnecessary spaces, you don't have indentation and extra characters that are not really helpful over there. There would be some other way by which it's easier for the computer to be able to sort of read and understand what is there in the specification. So in practice, what is done is, rather than just providing the DTS into the kernel, it is compiled into something else called a DTB, which is the device tree blob, and a blob stands for binary large object, right, or a binary object, right. So a blob over here in our case is going to be that you can take the device tree specification, the DTS, and convert it into a DTB. At some level you can think of it like writing a C program, which is good for humans to understand, compiling it into a .o file, which is assembly language instructions that are much closer to what the computer can understand. Of course, after that we still have the linking stage which converts it into an actual executable. In the same way, the DTB is loaded by the actual kernel in order to provide its actual functionality. Okay. So rather than talking too much about the background, I am going to straight away jump into this thing where we look at an example of a DTS and try to understand the different parameters that are present there.